Before I continue to tell you what this talk is about, I want to acknowledge my collaborators, Xuyang Ling, a brilliant guy now at NYU, Yang Li, a current student who will soon join Facebook and be a spy on the inside for me. This talk has two parts. The first part is very theoretical. It has to do with unsupervised learning, with clustering, with spectral clustering. And the second part is very applied. It has to do with classification, supervised learning, pushing AI to the edge, and deals with compressive deep learning. So if you don't care much about theory and not really about very applied things, there's nothing in this talk for you. Otherwise, let me start with the first part. And the first part, even though very theoretical, started with a very applied problem. We worked on a few years ago. In which context I actually was also visiting Michael to understand a little bit more about good models for MRI. We tried to understand if we can get some insight into Alzheimer's disease from MRI images. And the challenge there is you really want to get it very early on, not when Alzheimer's progressed a lot, but at the very early stages. And so you see these different MRIs, and you want to detect these subtle differences where, for me, unless it's progressed very much, I cannot really see the difference very much. So we had this bunch of MRI, 3D MRI scans, and put them into a diffusion map machinery that we developed, and wanted to see if somehow this unsupervised approach can distinguish Alzheimer's brains from non-Alzheimer's brains. And here's a typical outcome. You see, we put in 4 brains, 3D scans of a brain, sometimes run on different machines. So we took into account these calibration errors. And our method nicely spit out, the yellow one corresponds to the yellow and red are the Alzheimer brains, and the bluish ones are the non-Alzheimer brains, the healthy brains. So there's a clear separation. You can clearly distinguish them in this low-dimensional space. Seemed to work fine, and then sometimes the method did not work fine. And then I didn't really understand why. So this got me thinking, what is not working here? This was a complicated method working on complicated data. So of course I had to backtrack, build a simpler model, look at simpler examples. Diffusion maps are built on spectral clustering in a sense. So I thought, well, if I understand spectral clustering really well, maybe this is a starting point to build up and go from there to understand what we don't get right here. Spectral clustering has been around for decades, and I thought there must be plenty of theory that tell us about the performance of spectral clustering. Of course, there are tons of results on spectral clustering in terms of convergence of the graph Laplacian when you sample more and more data. Unfortunately, there's hardly any theory, to my big surprise, that tells you when spectral clustering will work and when it does not work and how well it will work. And I found it really disturbing because we use it all the time. We show these plots to the students. We say, K-means doesn't work in this case. Spectral clustering is much better. And yet there's not a single useful theorem that tells us spectral clustering works under these conditions and breaks down under these conditions after decades of using it. And I found that, to steal some slogans from Ron, I found it really disturbing and really uncomfortable. There are theorems out there, don't get me wrong. There are theorems out there that assume if the two clusters are infinitely far apart, I'm not continuing there. There are other theorems that tell you if you have a perfect adjacency matrix, I'll tell you later what it is, which means you have to know the clusters beforehand to design that matrix. But if I know the clusters beforehand, I'm not doing clustering anymore because I'm done. So these theorems are not really useful. And typically, these theorems are then followed up with statements, well, and then you use some perturbation results, and you get the other cases too. And that's not really true. And therefore, spectral clustering really begged for a rigorous analysis. When we started working on spectral clustering, we quickly realized that's, yes?
Normal spectrum of the matrix, spectral clustering.
I will tell you what spectral clustering is in 2 minutes. And it's related to other areas. This is, of course, well known. Community detection, graph cuts, all this is connected. These are all very hard problems, and we started working on this, but we got solutions, not surprisingly, for all 3 of them. Before I come to spectral clustering, let me tell you about the workhorse in clustering k-means. So the idea is we want to cluster points into meaningful groups. Now k-means is one way to do it. You minimize this objective function here where you try to find centers and you compute the L2 distance to the centers. You of course need to find the centers and you need to find the right partitions, so you have this optimization problem. It works sometimes very well and often it doesn't, and the limitations are very clear. The cluster should be within convex boundaries, and in addition, sometimes or very often this is overlooked, the clusters need to be isotropic. If I take two lines and make them really long, very far apart, but I make them really long, k-means will not work. They're linearly separable, convex, it doesn't work. So isotropic is important as well. If you have that, fine. If not, then not. And here's, of course, an example. What you would get with k-means, it would cluster the points in this red and blue, and another example where k-means would fail, and you would really want this, this to be one cluster and this to be another cluster. Of course, there's well-known remedies for this. Kernel k-means is one such approach, and it comes in many, many flavors. I just list a few names here. How you can approach it, let me jump right away to the one that we are using here, spectral clustering. Spectral clustering consists of two steps. One is we construct this Laplacian eigenmap. That's the first step. I will explain in a second. And the second step, which is necessary because your clusters are not infinitely apart and your clusters are not already known to you in advance, is after you have mapped them into this other space, you hope that k-means now does work because now things are nicely separable, hopefully. And then you apply in a second step, for example, k-means, or some other what we call a rounding step, because the output here should be indicator functions. They are not, therefore you could round them to indicator functions, therefore the name rounding. But the better way is to use k-means. But this two-step thing makes the theoretical analysis very tricky. So let me build up what is spectral clustering in case you're not familiar with it. We have a bunch of points. I colored them already in a way that should tell you what the clusters are, but the coloring is really just for purposes of illustration. In general, they're just points to you. And we construct a weight matrix, an adjacency matrix. This weight matrix measures similarities between points with this Gaussian kernel or some other kernel if you want, but let's use the Gaussian kernel. I take the distance, L2 distance, weight with some variance, and then take it to the negative exponential squared. So this is the standard Gaussian kernel, the heat kernel, and we construct the graph Laplacian, which is really the analog of the continuous Laplacian on graphs. As the difference between the degree matrix and the weight matrix. I can rewrite it, and you could see easier that it's really a Laplacian in a classical sense, discretized. But this is another way to introduce it. And when I said you need, in one bunch of theorems, you need to know the weight matrix in advance perfectly, it would mean you already assign weights of size 1 to these and weights of size 0 between points in different classes, which you don't know. So you cannot do that. And this graph Laplacian carries a lot of information about these data points if you think of them as a graph. In particular, the second eigenvalue tells us something about the algebraic connectivity of this graph. Now, what is then spectral clustering? Well, we construct the eigenvectors of this graph Laplacian L. Now we come to your question. We take the eigenvectors and I use them as a new coordinate system. Typically, I would not take all of them, but truncate them to have a dimension reduction as well, but I don't have to. But that's what I've listed here. I would take the eigenvectors associated with the k smallest eigenvalues. So that gives me an embedding in actually a smaller space, and it hopefully embeds this data set after running it through this nonlinear map into this, and then I do a simple k-means on this, hopefully. That's spectral clustering. And the pros and cons of spectral clustering, well, it has been around for many years. Empirically, it does often work better than k-means, even though we cannot really prove it. Not for a single example is there proof yet that it does work better than k-means, not for a single example. And there are cons. It's exactly, we have no theory for it, no meaningful theory. I talked with Joel before about meaningful theory. I'm not sure if I present really meaningful theory, but it's clearly much better than what is out there because it comes with clear conditions. So our goal is end this 30 years of, lawlessness in spectral clustering and bring in some order, some theory. The step here is to look at this weight matrix again. And we make a link to graph cuts. We motivate this from the point of view of graph cuts. So let's say I have a graph. You imagine all of links between points. Well, not all of them are linked. Some of them are linked, some are not. Some nodes in my graph may be connected, some are not. And they may be connected but have a very small weight, or they may be connected and have a very strong weight. And so it's not just 0 and 1, connected or not connected. It's not binary, but it could be strongly connected, weakly connected, or maybe not connected at all. And let's say I want to cut this graph into 2 parts so that I minimize the number of links that I cut when I cut this graph in 2 parts. And I can define this, of course, in a clean definition. I would define a cut through a graph by taking 2 parts of this graph, let's call it gamma and the complement, and then I sum up the weights that go across this path. So in this case, if my cut would be like this, I would look at all weights across this line, sum it up, and that would be the cut corresponding to this cut. If I cut it differently, I would get a different number. And then I try to minimize this cut, and that gives me the optimal graph cut. The problem with this definition is typically what you end up with is not something like what you have here, the green cut, but the red cut. You cut off one single node. And that often is the optimal solution to this. That's usually not what you want. Typically, you want to have a more balanced cut. But this formulation favors these cuts where you just cut off one single node. That's not really what we want. Therefore, let's balance this. We can introduce the size of the graph that we, the pieces that we cut it into, and define a so-called RatioCut. So we want to minimize this cut, divide it by the size of the subgraphs, and that balances the whole thing. For example, in the case of k equals 2, it looks like this, and this is much nicer. Unfortunately, it is NP hard in general. The other problem was very easy to solve. So the unbalanced cut is easy to solve. This is better, but NP hard to solve. There is an obvious connection to the graph Laplacian. We can introduce this indicator vector that has 1 when a certain index point, a certain node belongs to one part of the graph, 0 if it does not belong to that graph. And then I can write this cut simply as the graph Laplacian inner product with this, for the submatrix A, for this sub part of the graph, with this outer product of this indicator vector. And the RatioCut, by extension, in a similar way, where we have the size of the subgraphs below again. So the cut can be expressed in terms of these inner products. That's important for us. And this x here, that's the thing we're looking for, right? The L is what you construct, the x is what we're looking for. That's a block diagonal projection matrix. So this structure, keep in mind. And what we ask now is, well, since this RatioCut problem is NP hard, can we somehow relax it and make it solvable with as a semi-definite program? So what properties does this x satisfy? Well, I said before, this x looks like this. It's this block diagonal matrix with projections along the diagonal. But that's not really a matrix that we can easily enforce, so we need to see what we can do with it. Well, clearly this x must be positive semi-definite. It's entry-wise positive. This projection property is in part not completely, but in part captured by these 2 properties here. And all these are convex sets. So we could say, well, instead of aiming for the true x, let's aim for an x that satisfies only these 4 properties. And, well, this is not new, except for this little thing here. This is a standard convex relaxation of RatioCut. as I said, except for this little thing here. And I can rewrite it without this thing, and it becomes simply an eigenvector problem. We don't do that because that doesn't help us. So we need to throw in this tiny little condition here of non-negativity entry-wise and solve this problem. This is a semi-definite program. And now we can solve it in polynomial time. If you want to know how to really solve it fast, because polynomial time can be really, really slow, ask Joel. He told me he knows how to solve this problem reasonably fast and with guarantees. So this can be done reasonably well numerically, at least according to the expert. 2 more years, okay.
I'll start the algorithm.
Please. I give you 20 minutes. So we can solve this in the very near future. But the question is, does it do anything good? When is the solution to this convex problem that Joel can solve very fast in 2 years, 2 years from now, not in 2 years, when does it give us the correct solution? And that's the problem I want to, and under which conditions are these meaningful conditions, are these good conditions? So here, this is the key slide for this first part of the talk. How can we build a theorem that tells us when this STP solution solves the original spectral graph cut problem and thereby the spectral clustering problem exactly? There are 2 things that we need to think about. If I have a graph cut or clustering problem, 2 things matter. You know, if I want to, let's say I want to cluster this in 2 clusters, the reddish and the bluish. What justifies calling this red its cluster and blue its own cluster? Somehow the red points, orange points, this is red, this is orange. These orange points must be closer together than if I look from orange to blue. So somehow the connectivity inside here must be stronger than if I look across this red line. How can I measure this? Well, the connectivity within this subgraph can be measured by the corresponding second smallest eigenvalue of the corresponding subgraph Laplacian. So this LA corresponds to the graph Laplacian for this green orange set. So I look at the second smallest eigenvalue to somehow quantify the connectivity within. Now, if I say these are 2 different clusters, the connections between these clusters cannot be too strong. So how do I do that? Well, I could say, what is the, how strong is the link from here to this point, 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 and I do it for all orange points. I look at the connectivity to all blue points. One way to measure this is with this formula, the D, what we call outer max, the outer degree, then we take the maximum. So what do? I take a point here and sum up all the weights from this point to points that are not inside this cluster. So I sum up all the Wij's across, you know, from orange to all the blue dots, but not within the orange dots. So that's the second quantity. First quantity measures within connectivity. Second quantity measures, you know, with the across connectivity. This should be strong. This should be weak. Otherwise, we couldn't really justify these 2 clusters in 2 different parts. Here's the theorem. If this across connectivity is 1/4 the within connectivity, then this STP problem that we solve will solve the original graph cut problem, the original NP hat problem. So the solution that you get, if this condition is satisfied, it gives you the optimal solution. It is the correct thing. And therefore, you can recover this X, and from this X, I can exactly construct the clusters that I want. So STP really gives you the correct thing. So in this regime, NP hat is not NP hat anymore. And I should say this is purely deterministic. There's no randomness involved, no random model on the data. We don't assume Gaussianity or anything. It's purely deterministic. I could prove the same thing for normalized cut. You know, there's a similar thing as RatioCut, normalized cut. It is connected to random walks. A similar result we can prove there as well. And therefore, there's also a link to diffusion maps. Let me just give you a short game of Cohn's proof. It's really about duality theory. This is the optimization problem we have to solve. Using Lagrangian duality, we can rewrite this in this way. And we're looking really for a dual program. And we're very short on this for time reasons. But this is the thing that we have to target. And The question is then, under which conditions can this be true? And you need to do a lot of spectral theory to really get the right properties here. So I'm keeping this very short, but it's a lot of, in a way, classical Lagrangian duality, but the details are really what makes it very technical, and this turns into this 20-page proof at the end. Now, let's look at this condition. I claim this is a useful condition. Well, how good is it really? Let's look at these two examples that we always use to say, k-means is not good, you should use spectral clustering. This is such an example. These two concentric circles. I want to now show, can, under this condition, what I said, this STB problem recover these two clusters exactly. It's a toy example, but it's kind of a test case, a benchmark to see if my theory is any good. And of course, you have two distances here, the within cluster distance between red dots or between two blue dots, and the distance between red and blue, the nearest distance. These are the two distances that we have to keep in mind. The within distance, and what our theorem in this case, what do we have to do is we have to, let me come back to this, we would have to prove, we have to calculate lambda 2 for this particular case. We would have to set up the graph Laplacian for this case, compute the second smallest eigenvalue explicitly, and then compare to the corresponding distance in this outer degree, which we can compute. And it turns out that it's almost optimal. The minimal separation between points is of the right order. If this minimal separation is not justified, if the distance here is larger than the distance across, you have no justification to cluster the red points in one and the blue in the other, right? If the distance here is smaller than the distance within a circle, you cannot really justify it. But in our case, it's order optimal. So our theorem seems to be, in a sense, almost as good as it can be. Now, the proof for this very simple case with the two circles, a trivial example, as trivial as it can be almost, is another 5 pages simply to compute this lambda 2. So this begs the question, what can I do in general? I want to do maybe some more realistic cases where I have a manifold, I randomly sample from this manifold, maybe I have a model on this manifold, some smoothness. Can I prove something in this case? And this is still an open question. We can get some results, but we're far away from getting anything good. And this is really so far a very challenging problem. There's some literature in this direction, but it's all not good enough yet to really give us what we want. So this is still an open problem. I said we can do community detection as well. Let me give you an example. I use this stochastic plot model for the community detection. It's a standard model. I understand not very realistic, but it's really more a benchmark to see how good is our theory in this case. Now this is a probabilistic model. I assume two communities, and I assume that two members in a community are, two elements in this data set belong to the same community, and I pair them with a probability P. If they are in different communities, I pair them with probability Q. And then I build connections in this graph based on this model. And of course, I have to assume that P is larger than Q, and then I can ask, I give you now the adjacency matrix of this graph. Can you find the underlying communities? And of course, this is a well-studied problem. Our theorem in this case, we can apply it in this case as well. And the result says, yes, we can recover the two communities as long as this condition is satisfied. You see the alpha comes from here, the beta comes from here. These terms always show up in this community detection problem with stochastic block model. Now, how does this compare to the state of the art? The state of the art says you cannot recover it if alpha is smaller than this. But you can recover it when it's larger than this. So we are off by a factor of this constant 13. But keep in mind, we are not using any probabilistic results in our theorem. So ours is purely deterministic. Therefore, we lose a little bit. But at least up to a constant, our framework gives you the right result. It's also used for semi-supervised learning. But I think I will not say too much here. The point is sometimes I'm clustering points, and I show you a few labels. Let's say these MRI images. I have this huge set of MRI images. Some of them are Alzheimer's, some are not. I don't know. But getting a doctor to look at these images and look at it carefully and say, yes, this is Alzheimer's or not, is time consuming. So out of these 10,000 images, maybe only few are labeled. Let's say maybe 10 or 20 are labeled. So it's really not a classification problem because the number of training data is so small. We have classification, clustering, the two ends of the same question. In classification, it means I have a lot of training data. Clustering means I have no training data. And semi-supervised is somewhere in between. I have a few training data, I have a few labels. Can I use that information to improve my clustering? Well, the standard methods in semi-supervised learning for clustering in k-means would just mean, well, I choose a smart initial guess based on these labels, which is absolutely nonsense because you can even break it if I show you 99% of the labels. So this is not working. In our case, it's just an STB with a few additional linear constraints. So in 2 years, we can also solve this very, very fast. And you can then, this is just an example that we have here. I've made up a really mean problem where the clustering fails. I mean, it was designed to fail. And if I show you a few labels, it starts to improve fairly quickly. And so this is at least one approach to bring semi-supervised clustering closer into a reasonable theoretical framework. Second part of my talk, AI on the edge. This part has two motivations. One comes from something that some of you in the audience meanwhile know. Surveillance capitalism, the new threat to society, and I'm very serious about this, I'm not joking here. There's a great book by Shoshana Zuboff where she lays out in 700 pages very carefully this threat that we are faced by companies like Google, Facebook, Amazon, this constant surveillance we are subjected to, the violation of privacy that we are constantly subjected to, even though they say they're not. If you have a smart TV at home, you should know that it's recording you all the time. So be careful what you say in front of the TV. It may even film you all the time, so be careful. If you have a smart refrigerator, it will send information that you put out another bottle of beer to Amazon, and you will soon receive an offer from Amazon about maybe getting more discount on a beer. But it's not just prediction about our behavior, it's in meanwhile modification of our behavior. Facebook knows how to modify your mood. Amazon has patents how to modify your mood. Pokemon Go, a harmless game, was actually designed to see if Google can steer you in certain directions. So this is a real threat, in my opinion, to our society, and the question is what we can do about it. For time reasons, I will not say much about this, more than this really begs, just excuse me, why? Oh yeah, here we are. This really asks for privacy-preserving machine learning as what they call human imperative to combat surveillance capitalism, to move surveillance capitalism in a more humane way. Let me come back to this in a second. Let me jump to the other motivation first. A project I'm working on with a startup company has to do with AI on the edge. Oh yeah, this is why I need this. What do I mean with the edge? Well, you all know about the cloud. What is the edge? Well, the edge devices are your cell phones, tiny sensors, maybe your smart refrigerator. These are devices on the edge of the Internet of Things. You have the cloud, you have the edge. In between, by the way, you have the fog, but we're only talking about the edge today. Edge devices are great in the sense that if I can have my algorithm run on my little device without connecting to the Internet, I can keep my data private, preserve privacy, it's more secure, remove latencies, and I don't need to be connected to the Internet, so I can be off the grid. So therefore, putting machine learning on the edge, on edge devices, is a very popular theme. And ironically, it's also why Google, Qualcomm, and other companies are working on this. We came across this problem of putting machine learning on edge devices in a real-world problem. The problem I was working on really comes from the second part, but it's very similar in the first part. So let's start with the first part. Imagine a catastrophe, like an earthquake or some human-made catastrophe, and you have lots of casualties. The power grid is down, you have medical care units, the emergency care units coming in, try to saving human lives. You have many, many injured people, and what these medics have to do is take care of these people, help them quickly and get them onto some helicopter or some car and then ship them off to the next trauma center. Of course, some information has to be taken into account when I do this. When I'm a medic and then taking care of this patient and I'm administering, let's say, 10 milligram of morphine, somehow this information has to be recorded because otherwise the next doctor gives him another 10 milligram of morphine, another 10 milligram of the morphine, and the earthquake is the least of the problems of this guy. So you need to keep the information, what you do to this patient at hand. The problem they're facing is I have many patients here that I need to take care of quickly, and I have to stop and write things down. Do you spell your last name with a D or double T? So it's not really the right way to do this. So it would be great if I have a mechanism that automatically records what I say during my administration of this patient and adds it in the right place on some tag. And this tag gets passed on a helicopter, gets passed on to the hospital, and all the information is automatically of this patient collected there. It would save me one medical person to record data, and therefore I can move through the patients quicker. And the military wants to do a similar thing. You have to imagine a battlefield, and you have the para-rescue men, or PJs, how they call them, move in quickly, take care of the patient, move him out of the battlefield, put him on a tourniquet, maybe that he's not bleeding out, and that's unfortunately one of the things that happens quite often. Therefore, some soldiers already go in the battlefield with this tourniquet put on, so you just have to turn him if you really blow up. And when these rescue men come in, the military would like that these rescue men have this AI device that automatically records on this tag information what they do to this patient. And you cannot assume connectivity to an internet in this case. If you have your battle, you cannot really say to your enemy, I have 0 bars here, could we fight over there? Maybe I get internet connection there. You just, fight wherever you are. So you have to have this device that runs all these things, automatic speech recognition, object recognition on the device. No connection to the internet, so this little device, head-mounted display or some other device, has to do all the machine learning. And that's a challenge. It's a challenge because these edge devices are very limited in power, they're very limited in memory, and they're very limited in computing power. So battery life is limited, and that alone limits your computing power, but the chips that you have typically are also not very strong. With all these limitations, companies set out to develop special hardware in this case. People have developed special software solutions. Deep learning, there's a lot of work on on-device machine learning. Typical tools that we see are here. We realized when we tried to do this simple head-mounted display was overheating all the time simply by collecting data. So the amount of data we collected was already too large. We couldn't really use. These things are nice, they're great, but they don't suffice in our case. So we needed to reduce the number of data that get into our device beforehand, before we could do anything. And that brings up the idea of compressive machine learning. And let me give you one toy example before I lay out the real thing. Let's say you know already you want to classify objects into 3 groups, trees, cars, and people. In our case, it would be different medical medications, but let's just say it's 3 cars and people. So I'm walking around with my camera, and I'm recording trees, cars, people, other things, houses, cows, dogs, but I really care only about these 3 things. Therefore, and I want to only assign labels to these 3 things. And I don't care what tree it is, I just want to know it's a tree. I just want to know it's a person. I don't care what person it is. So let's say these are trees, these are cars, these are people. And what I really want to do is I want to sample all the trees just with 1 bit, all the cars with 1 bit, and all the people with 1 bit, because I don't care to reconstruct which person it is. I only want to assign the right label to all the blue points. I only want to assign the correct label to all the cars. I don't care about reconstructing that car. So therefore, this idea of compressive sensing, when I design a compression matrix that kind of samples everything in the entire space for all sparse signals, It's wasteful for me because I don't care about everything. I don't care about reconstruction. I only care about assigning a label to all cars. And I don't care which car it is. So very few bits should be enough. And I want to build this into my measurement process. So the sensor itself should already have this built in, that it only senses the things of interest to me. And so that's the idea of this compressive approach that we try to implement here. So it's inspired by compressive sensing, but compressive sensing works for all signals that are sufficiently sparse, and it gives you the ability to reconstruct. We don't care about reconstruction, and we don't care about all signals. We care about very specific signals. So we need to do some form of compressive sensing, but more tailored to classification, to the goal that we have in mind. The goal is not reconstruction, but classification. And therefore, the setup would be like this. Our sensor that is sensing this scene has built in hardware this specialized compression matrix that we will design. So it is like a compressive sensing matrix, but tailored to our needs. And then, we feed this, so that means in my device, I already get compressed input. Of course, what you could say, why don't you measure everything and then compress it? But this is what causes overheating. I cannot measure all this data and then compress it. Costs me memory, costs me computing resources, battery resources. So I need to have the data entered in compressive form already in the device, like we do in compressive sensing. But unlike compressive sensing, it's tailored to my needs. And then we run it, let's say, through some deep network classifier. So how do I construct this projection matrix that I will then later build into hardware? There are several ways. One is, well, you have a training data. Then construct simply a PCA matrix out of this training data, and that's your optimal projection in a certain way. We cannot really build this PCA matrix. It's an unstructured matrix. We heard today about sketching with Gaussian random matrices. Well, the devices we have in mind are extremely cheap. And so this has to be something that they can build easily in hardware. A random matrix I cannot really implement in hardware easily. But a convolution I could. And Justin knows a lot about random convolutions. This is not exactly a random convolution because it's a convolution that should somehow mimic PCA. So what can I do? Well, let's say I take my PCA matrix, P, and I want to find a convolution matrix that is close to this matrix P so that the subspaces are as close as possible. So I have one projection matrix that spans a subspace, and I want to find another structured projection matrix with convolution structure that spans as close as possible the same subspace. It won't be the same. So I want to minimize the angle between the two subspaces. This is my PCA matrix. This is a matrix that has some structure from this matrix space. In my case, it's a convolution matrix. And since it's a projection, I have this additional constraint. So I wouldn't have to solve this optimization problem. It's a form of Procastro's problem, right? Matrix optimization problem. Find the nearest matrix to a given matrix where this nearest matrix belongs to some space, algebra maybe, and we have this orthogonality constraint. Well, it turns out this problem is actually very hard to solve. But I can come up with one that is nearby, and I can simply rewrite this a little bit. And it starts to look like this. And then I can solve this problem, and I can solve this problem really, really fast. And this is the projection matrix that I'm using now. So I'm solving a nearby optimization problem. I'm using this projection matrix, which now has convolution structure. I can build this into hardware. I can add it to my sensor in front, and therefore the data enter in compressive form already. Just to give you one simple one example, because I'm running out of time, the standard MNIST test case here. Compression rate is here. This is the accuracy of classification. MNIST has images of size 28 times 28. That gives you 784 pixels per image. So a compression rate of 10 means I have about 70 pixels. A compression rate of 30 means I compressed my images of 28 times 28 down to 5 times 5 images. There's very little information left in this case. And yet you see, this PCA would be this. PCA I cannot really do in practice. This is what I would do if I would do standard compressive sensing. It doesn't really work very well. And this is one example of what I have shown you. There are other ways to do this, but this is just one example. So you lose a little bit in performance, but at least your system doesn't break down, and actually you can really run machine learning on device. There's always a trade-off. When you run machine learning on device, you accept it may have to give something because it won't work as accurately, but at least you want to get some decent performance. Just to wrap up, in the first part of my talk, I wanted to illustrate that there is indeed a rigorous mathematical framework for spectral clustering that gives you bounds that are almost optimal. The open questions, of course, are how can we improve something for semi-supervised learning in this context? How can we move to prove something for data coming from some manifold with a probabilistic model in the background? The second part of the talk was a step towards privacy-preserving machine learning, a very small step yet, but I think we have to do many more of these steps in order to really deal with this threat of surveillance capitalism. And that's a great opportunity for us mathematicians. We can really do something useful to turn this digital revolution into a more just revolution. Thank you very much.